Hey everyone, and welcome to this explainer. So today we're going on a bit of a visual journey to really demystify some of the core foundational concepts in physics. If you've ever looked at physics and thought it was just this massive, confusing jumble of equations, honestly, do not worry. Just think of me as your friendly tutor today. We're going to break things down step by step using some really clear, intuitive visuals to map out exactly how the world moves. By the time we wrap up, you'll be looking at everyday motion in a totally different way. I want to kick things off with a quick question for you. If you picture a car braking at a stoplight, or maybe a leaf just gently falling from a tree, how would you actually draw that motion on a piece of blank paper? We see movement literally every single day, right? We walk, we ride bikes, we watch things drop. But translating that real-world dynamic action into a simple line on a graph, that is basically the secret language of physics, and it's exactly what we're going to learn to speak today.
All right, let's dive right in. To keep things nice and simple at the start, we're going to focus entirely on motion in a straight line. Physicists call this rectilinear motion. I want you to imagine taking a journey down your street. You're walking, or maybe you're on a bicycle, in a perfectly straight path. There's no left turns, no right turns. You're just moving steadily forward, or maybe backward, along a single line. This really simple, everyday scenario is going to be the bedrock for everything we build on today.
Now, to track your journey down the street, we first need to know where you actually are. And that brings us to our very first key concept, which is position. Position is simply the location of an object with reference to a conveniently chosen origin. You can think of the origin as your starting line, kind of like your front door. To describe your position, we really just need that starting point and a way to measure the distance you've traveled away from it. It's basically the where of our motion story.
Okay, so how do position and time actually look on a basic line graph? I want you to visualize plotting our walking journey. Just picture a piece of graph paper. Along the bottom, on the horizontal axis, we have time ticking forward. 1 second, 2 seconds, 3 seconds. And then up the side on the vertical axis, we plot your position, meaning the distance you're climbing away from your front door. As you walk down the street, your line on the graph is going to move to the right as time passes, and upward as your distance increases.
But here's the thing. As you walk or cycle, you aren't just stuck at one position. You're changing your position over time. And this brings us to velocity. Velocity is defined as the rate of change of position with respect to time. Now you might be thinking, wait, isn't that just speed? Well, actually, velocity is a bit more than just speed. In physics, velocity cares about how fast you're going, sure, but it also really cares about the exact direction our cyclist is moving down the street.
So the absolutely crucial point here is this. When you look at a position-time graph, the slope of the line directly represents the velocity. Think about it visually for a second. If the line is incredibly steep, it means you're covering a whole lot of distance in a very short amount of time, meaning you're moving fast. If the slope is gentle, you're moving slowly. But what if the line is perfectly flat, completely horizontal? Well, that means time is ticking forward, but your position isn't changing at all. You are just standing completely still. Let's look at how we can put some actual numbers to this idea. Here's a simple set of data from our imaginary cyclist moving smoothly down the street. At 0 seconds, they're at 0 meters, which is our origin. After 2 seconds, they've traveled 10 meters. After 4 seconds, they're at 20 meters. You can see pretty intuitively here that they're moving at a nice, steady pace, covering the exact same amount of ground every 2 seconds.
Let's actually calculate what that pace is. And hey, don't worry, there is absolutely no intimidating math here. To find velocity, we just follow 3 super simple steps. First, we find the change in position. Looking at the whole trip, 20 meters minus our starting point of 0 leaves us with 20 meters. Second, find the change in time. 4 seconds minus 0 is 4 seconds. And third, we just divide that distance by the time. 20 divided by 4 gives us a precise velocity of 5 meters per second. See? Just basic division, no advanced math required at all.
But what happens to our whole story if the cyclist suddenly changes their mind? Let's contrast 2 actions, moving forward away from home versus turning around and heading back home. Remember earlier when I said velocity cares about direction? Well, this is exactly where that becomes incredibly important. In the real world, turning around simply means you retrace your steps. But we have to ask, how does our line graph handle this exact change in direction?
Honestly, it handles it brilliantly. A downward sloping line on your position time graph actually means the object is moving in the opposite direction. When you turn around and head back toward the origin, your distance from home is shrinking as time keeps moving forward. Mathematically, this gives us a negative velocity. So keep this in mind. On these graphs, negative doesn't necessarily mean you're slowing down. It simply means you've changed direction and you are heading the other way.
Up until now, our cyclist has been moving at a perfectly steady, constant speed. But let's pivot for a second to situations where our speed isn't steady, because, let's face it, real life is rarely that smooth. Think about an athlete exploding off the starting block in a sprint. Or think back to our earlier example of a car hitting the brakes at a stoplight. In both of those cases, the velocity is actively changing, and this introduces a brand new concept to our journey. That concept is acceleration. Acceleration is defined as the rate of change of velocity with time. Simply put, it's that literal physical feeling of speeding up, slowing down, or changing direction over time. Just like velocity was the rate at which your position changed, acceleration is the rate at which your velocity changes.
And I want you to notice how brilliantly this difference shows up on a graph. If you have constant speed, your position time graph is a perfectly straight, angled line. You're covering ground at a reliable, steady rate. But if you have acceleration, say you're speeding up, your line won't be straight anymore. It's going to be a line curving upward. A curved position time graph is basically the undeniable signature of changing speed. It literally means that in every passing second, you're covering more distance than you did in the second before.
So, what about slowing down? When a car brakes at a stoplight, its forward velocity decreases. In everyday life, we often call this deceleration, but in physics, it's really just acceleration working in the opposite direction of the motion. If your car is moving forward, but your acceleration is pushing backward, you are absolutely going to slow down. The sign of the acceleration simply depends on whichever direction you decide to call positive.
Okay, let's go ahead and pause our horizontal journey down the street for a moment, and let's look up. We've mastered walking, cycling, and braking cars, but what happens when objects move vertically? Well, it is time to introduce one of the absolute most famous forces in the universe into our straight-line motion story, and that is gravity.
To really understand vertical motion, we kind of have to look back at history. The great physicist Galileo Galilei made a completely groundbreaking discovery. He studied freely falling objects and concluded that the rate of change of velocity with time is a constant of motion for all objects in freefall. Basically, what Galileo realized is that no matter what the object is, if you drop it, gravity acts as a constant, uniform acceleration pulling it downwards. And the really amazing part here, he realized this hundreds of years before we even had cars or bicycles to track.
To make this abstract concept feel a bit more real and intuitive, picture that falling leaf we talked about at the very beginning of the explainer. Or imagine tossing a tennis ball straight up into the air. When the ball leaves your hand, it's moving fast, but gravity is immediately pulling down on it. It is exactly like that car applying the brakes. Gravity is acting as a constant downward acceleration against the ball's upward velocity.
And physicists have measured exactly what that constant pull is. Near the surface of the Earth, gravity provides a constant downward acceleration of roughly negative 9.8 meters per second squared. The negative sign is literally just there because gravity pulls down. This constant acceleration is the exact reason why a tossed ball slows down as it goes up, completely stops for just a tiny split second at its highest peak, and then speeds back up as it falls right back into your hand.
Which brings us to our final, somewhat provocative thought for today. I want you to think deeply about that ball at the very top of its arc. We know that for a brief instant, it completely pauses. Its velocity is exactly zero. But here is my quick question to test your brand new physics intuition. If a ball thrown straight up has zero velocity at its highest point, does it also have zero acceleration? I really want you to think about what is constantly pulling on that ball, even when it's standing completely still in the air for that split second. Ponder that, and I hope it leaves you super eager to explore even more of the beautiful rules that govern exactly how our world moves.